Hello, today in this lesson we are going to continue the study of the motion of a particle that is under the influence of a gravitational field that is uniform. Okay, so we are going to construct the Hamilton-Jacobi equation for this system, and recall that we have already made another lesson about this topic, and in this lesson we showed that the Hamilton-Jacobi equation for this is 1 divided by 2m times the partial of s with respect to x squared plus the partial of s with respect to y squared plus mgy plus the partial of s with respect to time equals to 0. Here is easy to identify that this is actually, well, the Hamiltonian of the particle, but with the piece changed for these partial derivatives with respect to x and y, right? For the generating function s. Okay, and I'm going to leave you in the description of the video the link to that first lesson where we start to study this physical system. So what we are going to do now is to solve this equation with a different method. Okay, we are going to make a change of a variable in this equation by noticing that we can express the quantity mgy plus the partial of s with respect to time as the partial of, well, the quantity s plus mgyt, right? So we have been also working with this kind of change of variables where we, in other examples, we name these quantities that we introduce with the letter s tilde, right? So we are going to introduce the change s tilde equals to s plus mgyt. Okay, perfect. So what are we going to get if we take this change of variable into the Hamilton-Jacobi equation? Well, first of all, looking that we have the derivatives of s with respect to x and y, well, from here we can say easily that s is equal to s tilde minus mgyt. And this takes us to have that the partial of s with respect to x is equal to the partial of s tilde with respect to x, and the partial of s with respect to y is equal to the partial of s tilde with respect to y minus mgt. Okay, perfect. So we are going to take these results into the Hamilton-Jacobi equation to get 1 divided by 2m that multiplies the partial of s tilde with respect to x squared plus, and here is the partial of s tilde with respect to y minus mgt squared plus, and here is where we are going to use this formula, right? So this is equal to the partial of s tilde with respect to time equals to 0 because this thing is s tilde. Okay, perfect. So with this we have found an equivalent Hamilton-Jacobi equation for the particle in the uniform gravitational field. And as we have been doing in recent lessons, we are going to notice that this equation does not include the element x and y, right? We do not have the x explicitly in the expression, and the y is also not present. So that means that we can propose a separable solution as s tilde equals to, well, it will be a linear function in x. So let's say p1x plus p2y. Recall, looking that x and y are not included in the Hamilton-Jacobi equation, we can propose a linear function corresponding to that variable. Okay, so, and for the time, looking that it is present here, well, we need to propose a general function f of t, right? So if we calculate the derivatives, we will have that the partial of s tilde with respect to x is equal to p1, the partial of s tilde with respect to y is equal to p2, of course, and the partial of s tilde with respect to time will be equal to the derivative of f with respect to time. Looking that f is a function of only the time, right? So we are going to take these results into the Hamilton-Jacobi equation to get that this is 1 divided by 2m multiplied by p1 squared plus p2 minus mgt squared plus the partial of f with respect to time, and this is equal to 0. Okay, so with this we can see that we have a differential equation for the function f, that is our variable, and well, it only depends on the time, alright? So this is kind of like a very easy to solve differential equation. We can see here that, well, the derivative of f with respect to time is going to be minus 1 divided by 2m p1 squared plus p2 minus mgt squared, like this. And well, to solve this, let me develop all this expression to get p2 squared here, then minus 2p2 mgt plus m squared g squared t squared, like this, right? And then, well, we can just take the integral to get that f is equal to minus the integral of dt divided by 2m and times, well, all this expression, right? So let me copy it to make it faster. Here it is. So, well, it is a very easy integral to solve. This is going to give us that f is equal to minus, it will be, well, we have these two constants, so this will be like a p1 squared plus p2 squared times t divided by 2m, right? And then we will have, well, this minus with this minus is going to be a plus, and then these two cancels with these two over here. So we will get, and this m can cancel with this m, right? So we will get p2 gt squared divided by 2. And then we will get a minus here, we can cancel an m. It is divided by 2, right? G squared, and then t to the third power divided by 3. But with these two, we will get a 6 here, right? Okay, perfect. So this is the function f of t that corresponds to the proposal of solution to the Hamilton-Jacobi equation that we made. And then, well, if we construct that function, well, we know that it was s tilde equals to, well, p1x plus p2y, and then minus all, well, plus all these function, right? Let me copy. Yeah, I think we will have something like this. And remember that we defined that s tilde is related with s with this equation. So to get s, we need to subtract this quantity minus mgyt, right? So we are going to say that s is equal to, well, all this minus mgyt. And let me copy this. Perfect. So this is the full expression for the s. This, well, we can say that this is already the solution to the Hamilton-Jacobi equation for the particle that is in the influence of a uniform gravitational field. Remember that there are some equations that define this function s, which is, remember, that is a generating function of a canonical transformation that, well, it satisfies these equations. This one, and qi equals the partial of s with respect to upper p. Okay, so we need to take these equations. These ones are to find the solutions to the equations of motion, and then if we find these ones, well, they are going to be helpful to find, well, the solutions to the equations of motion, but for x and the y, right? We will be able to know what is the motion of the particle in the x direction and the y direction if we, well, we manipulate these expressions first. So we can say that, for example, px, little px, right, is going to be the partial of s with respect to x. So if we take that derivative, we can see easily that this is going to be p1. Okay, so we have that px is equal to upper p1. Remember that we have been telling that, well, the upper variables, the capital variables, p and q, well, they are constants of motion. Okay, we have been explaining why these letters are representing constants of motion. So the thing here is that px is going to be a constant, which is something that we should expect, looking at, well, the particle, well, is in free fall on a uniform gravitational field, but the motion that is accelerated is only on y, right? So in x, there is no acceleration, so that's why the linear momentum in x is a constant. Okay, so this is a result that should be expected. Perfect. So with py, we will have that partial of s with respect to y. And then, well, if we take the derivative of s with respect to y, we'll first take here p2, And then what are we going to get? Well, you can see here that the y only appears in this element. So if we take the derivative with respect to y, we will get minus mgt, right? Like this. Okay, perfect. So we can say that py is equal to p2 minus mgt, and that p2 is equal to py plus mgt. Okay, perfect. These are going to be important results. Perfect. So we have now found what are the linear momentums in x and y. So now let's continue with the q's. What is going to happen with the q's? Well, q1 is equal to the partial of s with respect to p1. Okay. So if we go back to the s, the partial with respect to p1 of this, well, it's going to affect this element and this element, right? So we will get x and then minus p1t divided by m, right? So this will be x minus p1t divided by m. Okay, so what we can say about this is that noticing that we already found what is p1, that is px, right? Due to this equation, we can say that q1 is equal to x minus pxt divided by m. Perfect. So with this, we have found q1 in terms of the initial variables x and px. And then q2 is going to be the partial of s with respect to p2. Okay, so what is that going to be? If we go back to the s, well, we have a p2 here, we have a p2 here, and here. Okay, perfect. So we are going to get that q2 is equal to y minus p2t divided by m plus 1 divided by 2 gt squared, right? This is what we find for q2, and with this we have already completed the canonical transformation because we already have what is p2, p1, q1, and q2. Okay, so, but well, we are still need to express q2 in terms of the little variables, because here we have an upper p2, right? So we need to change that. So p2 is equal to this, py plus mgt. So we will have here that this is y minus t divided by m times py plus mgt plus 1/2 gt squared, alright? So this is y minus t py divided by m, and then minus, it will be gt squared plus 1/2 gt squared, and then this is going to give us that q2 is equal to y minus t py divided by m minus 1/2 gt squared. Okay, and you can see easily from this equation that we can solve for y to get the motion in the y direction, that is going to be q2 plus t py divided by m plus 1 divided by 2 gt squared. And well, you should know from basic physics that, well, this is very similar to the equation of motion of a particle in free fall, right? Where we identify this, for example, as, well, the initial position, maybe y naught, and we identify this py that we have here maybe as the mass times the initial velocity in the y direction, making that this element can be seen as, well, the initial velocity times t, right? So this expression is equivalent to y equals y0 plus the initial velocity in y times the time plus 1 divided by 2 gt squared. So yeah, for you to look it easier, well, this is the very famous equation for the motion in the y direction for a particle that is in free fall. And for x, well, we can just say from this equation that x is equal to q1 plus pxt divided by m. This is the equation of motion in the x direction. Okay, perfect. So yeah, there is another, maybe not necessary method, but another way to solve the motion of a particle in free fall, right? Perfect. So after finishing this lesson, I want to show you an example of Well, it's like a generalization of this method. I mean that we are going to take a particular Hamiltonian that can be, well, it represents many types of Hamiltonians actually for different mechanical systems. And that Hamiltonian is defined as h equals p squared divided by 2m minus phi of tq. Looking at, well, this is a function of the time, but I'm not giving an explicit expression for this phi. I mean, this is a general expression. So what we are going to do is that, well, we can use the method that we have used recently in this example to solve the Hamilton-Jacobi equation corresponding to this kind of Hamiltonians. Okay, so first of all, we are going to write easily what is the Hamilton-Jacobi equation corresponding to this. So that is going to be the partial of s with respect to q squared divided by 2m minus phi of t q plus the partial of s with respect to time equals to 0. Okay, perfect. So here we have the derivative with respect to time of the function s. We are going to be interested in taking all these elements that we have here and put them into the derivative with respect to time, like we did at the beginning of this lesson in the example of the free fall of the particle. Right, so we are interested like something, well, doing something like this. It will be maybe s plus something, right? So how are we going to do that? Well, looking that we have a function of the time here, well, this q can be considered a constant, and we are going to be taking the derivative of this function. But we should not modify the structure of the equation, right? It has to be the same. So what happens if, for example, we take the derivative with respect to time of maybe minus q times the integral of phi of t dt? Well, and then, well, we sum the function s. Well, we can say that this can be seen as minus q phi of t plus the partial of s with respect to time, right? Other way we can see it is that, well, we can take this t out, we can put maybe an x here, an x here, and then we evaluate the integral at t, right? Because when we take the derivative of the integral, we will only get the function that is inside. So the thing here is that we can make the change of variable s tilde equals to this thing that I have here. So we defined s tilde as a minus q, the integral of phi of x dx, and then plus the function s. So if we do that, look that, well, we need to take the derivative of s with respect to q. So the derivative of s with respect to q, if we solve this for x, we will take this integral to the left-hand side, and then, well, the derivative with respect to q will only give us this integral, right? So that means that, well, the derivative of s with respect to q is equal to the derivative of s tilde with respect to q plus the integral at t of phi of x dx. Perfect. So with this, we can take this into the Hamilton-Jacobi equation for this piece to get 1 divided by 2m that multiplies the partial of s tilde with respect to q plus the integral at t of phi of x dx, all this squared, and then plus, yeah, the partial of s tilde with respect to time, right? Because we had this expression, but that is equal to the derivative with respect to time of this, which is s tilde. So the thing here is that you can notice that the function of the time is not multiplying any q. Okay, I mean that in this structure we do not have anything like q times t or q times t to the third power maybe divided by 4. I don't know. I mean that there are no functions of q multiplying functions of the time, right? This is what we don't want, because if we have this, we are not able to use the method of separation of variables. So with this structure now, it turns out that we can use that method because, well, we do not have a multiplication of functions of q and functions of the time. Okay, perfect. So I hope this will be useful in some future examples. And well, I think it's an important fact to mention about the Hamilton-Jacobi formalism. Perfect. So I think that's the final important result of the lesson. I hope you enjoyed the video, and I think I will finish right now.